Hi, I'm Sarah, and you're about to learn how I scanned this here helicopter. The goal of this project was to demonstrate the fundamentals of remote sensing by building a functional LiDAR sensor and using it to 3D scan an object on campus. The target I picked was the Huey helicopter behind the Rotorcraft Center on campus. I picked the helicopter because it's a cool attraction the university has, but not everybody knows about. Also, I thought it would be cool to 3D scan a helicopter. Since it's so large, I focused on scanning the front half. Traditional LiDAR sensors measure range by timing how long it takes for a pulse of light to travel from the emitter, reflect off the object, and return to the sensor. The range is calculated using this formula: the speed of light times the travel time divided by 2. The LiDAR equation expresses the number of photons received as a function of the number of photons transmitted. The LiDAR sensor I built is a geometric LiDAR. Geometric LiDAR sensors work by putting the transmitter, in this case a laser, and the camera, which is the receiver, a set distance away from each other. If the object the laser is hitting is far away from the sensor, it appears more towards the center of the camera frame. If the object is close to the sensor, it appears more towards the edge of the camera frame. Using basic trigonometry, you can derive this equation for range, where PFC is pixels from the center of the image, and RPC and RO are correction values determined from calibration. My sensor is an active sensing design, meaning that it sends its own signal, in this case, a laser beam. A passive sensor doesn't transmit a signal, but instead senses a signal from the environment, such as sunlight. Here's my sensor design. The line laser, which functions as the transmitter, is located here. The camera, which acts as the receiver, is mounted 12 inches away up here. The Arduino powers the line laser, and the Raspberry Pi controls the camera. These are all powered by this battery pack here. I also have a phone attached for angle measurements. The chassis is 3D printed out of PLA in 2 parts, and the dovetail joint is assembled with super glue and hot glue. The chassis is screwed onto the 3D printed tripod adapter, which is then screwed onto my tripod. To calibrate the single beam laser, I set my laser and camera on a table 12 inches away from each other, as shown in this schematic. I then held a piece of paper at 6-inch intervals away from the camera, taking a picture at each interval. The line laser was calibrated in a similar way. I placed the laser 6 inches from the wall and moved it away in 6-inch intervals, taking a picture at each location. The data from these calibrations was processed with computer vision, i.e., training the computer to interpret my images. This was achieved using color masking and edge blurring in Python. I plotted the output data as shown and adjusted the RO and RPC values until I had a good fit. In this case, the red line is the output data of the single laser design, and this graph is the line laser calibration curve.
This is my setup for scanning my target. Here I'm set up on the inside of the helicopter, scanning the gauge cluster. So I have everything connected wirelessly via a hotspot on my phone connecting the Raspberry Pi and my laptop, and I'm working off of a VNC here. The process just goes, I have a particular angle here set, and then I check out my angle readout from my phone. In this case, it's 2 degrees, and I will put that into my prompt. So we'll run this, we'll enter our IMU angle, and let that run. So here I'm currently scanning the front side of the helicopter. There is some ambient light from these street lights, which I have attempted to block by setting up these tarps here. The other issue I'm having is with the reflectivity of the black paint. Like there you can see the laser is very, very hard to see. So I've had to adjust my settings, increase my exposure to get things to show up. Here I am scanning the front of the helicopter. There is a significant glare from the streetlight there, which I had blocked out with a tarp strung from the top of the rotor to one of these bushes. Unfortunately, we took the tarp down before I filmed the video. So the main challenge with this part is that the laser is very hard to see under the body, like nose of the helicopter. But up here it is a little bit better. Now, one thing to note about this is that in this orientation, I have my tripod at its full height, but helicopter is up pretty high. When I'm scanning at the very top, it's at a pretty significant angle. So there will be some distortion in the data because of this like high angle. So it'll look like the roof is a little bit lower than it actually is. So as you can see down here, the laser is basically impossible to see. Even to my own eye, it's really hard to see. But once you get past a lip, then it reflects pretty well. I've tried changing the exposure. This is 2 million. When I go to 3 million, the picture gets darker. So I don't know what's up with the exposure. I have my pictures here. For the most part, they turned out pretty well. The line is nice and bright in a lot of the pictures, but it doesn't reflect very well in some of them, as I discussed, like right here. It's very hard to see. So I went through each scan of each side of the helicopter and developed its own HSV mask. I use Color Picker to create the HSV mask. So you can see I selected the dull one here to make sure that I would be able to get all of those lines in there. And then I put those values here and ran that data through the data generation code to get my text file.
In MATLAB, I first imported the data from the text files. Next, I assigned the data to variables. Then, to align the scans, I translated the scans and rotated the scans. I aligned the scans using trial and error and comparing my point cloud to photos of the helicopter. Next, I cleaned the scans by setting all the points past a certain value to 0, 0, 0. Here is an example of the right side scan before cleaning on the top and after cleaning on the bottom. You can see the scan picked up the opposite side of the helicopter here, but it is noisy as you can see how thick the line is. I used this data to help align the scan and then filtered it out to have a cleaner point cloud. Finally, I plotted the data using the PC show function. And here are my results. This is the inside of the helicopter with the point cloud depth color-coded, so you can see some detail in the gauges here, as well as the center console coming out at you. This is the left side of the helicopter. There is some plastic in the window here that was picked up by the scan. This is the front of the helicopter, and here is the right side of the helicopter. Now you can see the side of the chair here, as well as the joystick here. And finally, here it is all together. The control panel on the inside is in cyan, and the outer surfaces are in the darker blue. I think the scan looks pretty representative of the helicopter, and overall, I'm pretty pleased with my results.
Mesh creation was a unique challenge for my scan because my object has internal geometry. First, to import the data into MeshLab, I needed to convert my data into a point cloud format. To do this, I used the point cloud function. Next, I denoised the data with the PC denoise function to help prevent noisy data from throwing off the normal calculations. Next, I used the PC downsample function with a box filter size of 5 to further denoise the point cloud. Then I exported the data into a .ply file. Next, I opened this up in MeshLab. I found the best mesh I got was when I just used the front scan of the helicopter. If I tried to use all 4 sides, it turned into a blobby mess. So to create a mesh, I went to Filters, Compute Normals. I used a neighbor num of 14 and a smooth iteration value of 1. And then I went to Screen Poisson Surface Reconstruction, and I used a reconstruction depth of 10, minimum number of samples of 1.5, and interpolation weight of 4 to get this result. You can see it has the general shape of a helicopter, but definitely has some blemishes.